Hello everyone, my name is José Eduardo Bueno and the title of the work I'll be presenting today is SPAI preconditioners in OPM Flow. So just to give you a general idea of what OPM stands for, it stands for Open Porous Media, and its idea is to unite open source software, open data sets that can work with industry standard inputs and outputs for reservoir simulations and related activities in order to provide an open innovation and reproducible research on modeling and simulation of porous media processes. So the main idea of OPM and OPM Flow more specifically is to provide an open source alternative and drop-in replacement for contemporary commercial simulators, and also to provide a research and prototyping platform that enables its users to implement, test, and validate new models and computational methods in a realistic industry relevant setting. So just to give an overview of what a reservoir simulator does. It of course starts with the physics, with all the geological information, the fluid behavior, and the wells and production facilities. And all this, in order to your computer to be able to work with, has to be discretized in space and time. And as these relations are complex, these discretization will result in nonlinear discrete equations, so they must be linearized. And this is done via Newton-like methods and numerical differentiation, which later has to be solved with linear solvers, which involve matrix operations and preconditioners. So the specifics for OPM Flow regarding the physics, OPM Flow uses the black oil model with oil pressure and water saturation as primary variables, as well as this X variable, which can be either the gas saturation or the gas oil ratio or oil gas ratio, depending on the properties of the fluid. And this X value can change along the simulation and can change also for the different cells of your model. So when you go to the discretization and linearization steps, Flow adopts finite volumes for the space discretization and fully implicit method for the time discretization, and an adaptive Newton-Raphson method in order to work with this possibility of change in the primary variables along the simulation. And for the numerical differentiation, it is adopted this upwinded 2-point flux approximation method, which is illustrated in this figure here, where the numerical differentiation is calculated based on focus elements and its neighboring elements based on volume fluxes. And now regarding the linear solver, the linearization from Flow builds a blocked Jacobian matrix. What I mean by this is that the Jacobian matrix from OPM Flow does not have scalar values, but has matrix values. So its elements are in itself submatrix, dense matrices. But the Jacobian matrix is sparse and ill-conditioned, as there are a mixture of variables with different numerical orders and different orders of magnitude. And OPM Flow uses the Dune linear algebra backend and the BICG stab linear solver, and has an ALU0 preconditioning as default. So here I present a result of profiling simulations with OPM Flow. These results are regarding a ensemble of simulations, so these are average values, but it is illustrative in the sense that it shows us that the linear solve time is dominant along a simulation, taking almost 70% of the simulation time. And going deeper on the linear solve, we were also able to conclude that applying the preconditioner and the sparse matrix vector problem products take the most time on the linear solve, with applying preconditioner taking almost around 40% and the sparse matrix vectors taking around 50% of the time of the linear solve. So, why add a new preconditioner to OPM Flow? First and foremost is that parallelization is desirable, as we saw the linear solve and applying preconditioner is a costly phase. The second reason is that the ILU0, the default preconditioner, is hard to parallelize. And there's also an absence of tests with preconditioners that are not previously existing in the Dune backend. And adding new preconditioners open up possibilities to research on multi-preconditioned linear solvers. So here is to give an idea of how the sparse approximate inverse preconditioner works, how it is built. Initially, we have to look at the rows of the matrix. Here's an illustration of a sparse matrix where the dots are the non-zero elements. So, taking a look at the zeroth row, we can form this J0 set, which are the indices of where there are non-zero elements on this row. And then, once we found this set, we go on each of these elements and look where there are no non-zero elements on the corresponding columns. And then we take these values, where there are non-zero values, we condense them in a set called I. So here is the I0 set, because it is corresponding to the 0th row. And then we take these elements and form a submatrix, as illustrated on the right here. This submatrix, then we need to solve a least squares problem with it in order for us to get the column of the preconditioner. So we can enhance the quality of this preconditioner by adopting the sparse dependent of the squared of our original matrix. And if we do this, we'd end up with the SPAI1 preconditioner, as illustrated here. The SPAI1, the submatrices for the SPAI1 preconditioner are larger, so the least squares problems are tougher to solve, but the quality of the preconditioner is better. And we can find this sparse dependent of the squared of the matrix using some graph theory and looking at the neighbors on this graph that has degree lesser or equal than 2. It is a pretty much straightforward computation. So here I start to show the results that I got working with the SPAI preconditioner in OPM or with OPM derived matrices. I implemented this preconditioner based on Dune, so it has Dune compliant semantics. What I mean by this is that it employs a lot of STL, C++ functionalities, and also metaprogramming. And there is, actually I have implemented this as a Dune module. There is a merge request going on for this implementation, for it to be integrated into Dune as well. And it is already, this implementation is already partially integrated into OPM Flow, and there is a draft pull request already going on for this as well. And all the tests I did for this work were based on the OPM test repository from OPM Flow. This is where all the open data sets are. So here are the results for the comparing total solve times for different matrices, for different reservoir models with different number of active cells as shown on the x-axis. The idea here was to compare ILU0 with SPAI0, so no fill-in for these, and ILU1 with SPAI1, now taking the square of the original matrix for building the preconditioners. So here we can see that for the ILU0 and SPAI0, there was a certain advantage for SPAI, but the performances were quite similar. But when we go to SPAI1 against ILU1, we can see more dramatic differences in performance favoring the SPAI preconditioner. So here's a condensation of the results presented in the previous plot. So here's showing the acceleration. This is the time that ILU, the solve took with ILU divided by the time that the solve took with SPAI. So we can see that SPAI has an advantage. SPAI was able to accelerate these simulations, these solve times, reaching a maximum of 10 times acceleration. So here are comparing the total iterations for reaching the solutions. Again, we can see that for all cases, SPAI0 and SPAI1 was able to achieve better performances with less iterations for the linear solver, and again more dramatic differences for SPAI1. So here it is comparing the reduction in the number of iterations for the linear solver. We got a maximum of 86% reduction in the number of linear iterations for SPAI0. So this is, we can conclude that the SPAI has promising results even without parallelism. And as future step for this work, it is of course to implement the parallelism and then to experiment with larger problems. And also, SPAI is a pretty flexible preconditioner. We can also experiment with different sparsity forming schemes, so perhaps reach even more performance gains. So this is it. Here are some of our sponsors. Thank you.